Swayam Prabha. Digital India. Educated India.
I want to sort of start thinking. So what I've done is that all I've done is the very preliminary time scales, length scales, and those kind of nature that I've done. Now I want to talk about one of the interesting things with particulate stuff. Why is it not showing? Oh yeah, it's slow. Okay. Now in the next couple of lectures, I want to talk about, and let's start thinking about the fact that particles are not in an array. They are not on a lattice. They are naturally going to be randomly distributed. So we need to think of, now I'm not even talking about the fluid. So in other words, imagine that you have a multiphase flow and you take pictures of it. All you see is a distribution of particles. Okay. Now I want to sort of walk through, how do you describe that thing? Is it uniform random? Is it clustered? How do I describe this is the kind of question that I want to start thinking about. The other thing is that when you have a multiphase flow, even if the flow is say micron sized tube and the flow is technically laminar, even if it's laminar, you're going to have pictures like this. Okay? So in other words, no two pictures that you take of your flow are going to look the same. They are going to be, so you have to think in terms of ensemble. So whatever concept that you will have for turbulent flow that we need in multiphase flow, even if it is so-called laminar. So there is random particle distribution. In a turbulent flow, you have two sources of instability. If you remove all the particles and you have to take pictures of turbulent eddies could be anywhere. So you have a ensemble of turbulent states. Now suppose you capture the turbulence exactly the same at two different instances. Suppose, I mean it's not possible. So in other words, you are saying I have the same turbulence. Now you say even then there will be variation from one instant to another because the particles are randomly distributed. So there is two sources of randomness that you want to think about. One, turbulence, and on top of this particles being randomly distributed in that turbulence. Okay. So that's why I said that ensemble is the product of the two, and they are also going to be related in a way. More particles could create more turbulence could spin out particles, and so on and so forth. So in other words, it's not like they are decoupled, but at least I want you to think in terms of that in a multiphase flow, turbulent multiphase flow can be doubly more complicated. Okay. Earlier we talked about how do you describe these things. There was a question. So I'm slowly building up what mathematical machinery we would want to describe turbulent multiphase flow. Well, for continuous phase you have the standard U, pressure, temperature, and so on. And for particles, again you have its position of the jth particle, velocity of the jth particle, and angular velocity of the jth particle, temperature of the jth particle, and so on and so forth. And if you take care of all the particles, the j goes over the trillion particle that you may have, you have a complete description. So in other words, multiphase flow is really not that hard in some ways. If you can describe Navier-Stokes equation outside of your trillion particles and you can keep track of the trillion particles, how they move, there is nothing profound. I mean, it's just, we have all the equations, you just can't solve them. We got to simplify. So much of the difficulty comes from averaging, because we cannot put grid around trillion particles. So in some sense, the kind of problem that I'm talking about, now there may be problems for biological activity happening, electrostatics, etc. There may be other complicated physics which could make the problem very hard. Most of what I'm going to talk about is if you were to have incredibly powerful computer, you can solve the flow around all the particles, and you track all the particles solving equations, and you're done. So much of our challenge really going to come from averaging. Okay, so that's something that I want you to think about. Now, the indicator function is nothing but so basically one of the techniques people use is they use an indicator function, which is a function of space and time, and the indicator function will be 1 when fluid is occupying and 0 when particle is occupying. So indicator function is a tool. It's sort of like separating particles from the surrounding fluid. Okay. So that's this ID is nothing but the indicator function. Now, I want you to, the other thing I want us to think about is a volume averaging versus ensemble averaging. Okay. The volume averaging is nothing but you take a tiny little volume and you average your indicator function. So in other words, you can average over all the particles in there, or you can average over all the fluid in there. So you can define, say, volume fraction occupied by the continuous phase, volume fraction occupied by the particulate phase. Say, for example, this volume fraction of the particles dispersed phase, you could sort of take an average of the indicator function and you can get it. So this is a simple way of sort of averaging, sort of coarse graining. Okay. So in other words, if you want to fuzz out a little bit, you sort of take a volume and say, I really don't want to worry about the details that are inside this volume, I just want to do an average. Okay. And that's what I said earlier, that's what you'll have to do. If you can put a grid of 100 by 100 grid points, you can't cover everything. So you're averaging. There is nothing that you can avoid about that. Therefore, you're going to do the averaging, and this is what I call as volume averaging. Now, you do the volume averaging of one realization. So in other words, if you do a volume average of this guy, you get a volume fraction like this if the particles are there. So you can see that volume average preserves some of the underlying structures that you see. So this is what is called coarse graining. So you coarsen. You don't worry about exact particles, what they are, but you do keep the big picture of where the particles are clustered and so on and so forth are retained. This is a very useful picture because if you do an ensemble average, as I will show later on, if you do an ensemble average of these things, you will get a uniform kind of stuff. What the volume averaging does is it preserves the structures that you see when you do the experiment. It just fuzzes out a little bit, but keeps some of the instabilities and clustering and fingers and other things that forms are retained. So I will emphasize a lot about this volume averaging technique. Now, volume averaging can be used.
Pay for the volume averaging. Is that something to do?
How big is that volume averaging volume? That's a great question. That is the rub there, is that how big it needs to be. Okay. So the rule of thumb I will tell is it needs to be much bigger than interparticle separation, because if you don't want to put a volume and no particle is there, or suddenly a particle, so it needs to cover several hundred particles in there to get meaningful average. But on the other hand, if you too big, then you may average over some of the structure that is there. By the way, this is an open question. There is no satisfactory answer I know of in the literature. Okay. So the volume averaging can be done. You can define particulate velocity. Now, these are Lagrangian particles, so each of them have their own velocity, I earlier said. But if you fuzz out, the good news is that you don't have to track trillion particles or so, but you come up with particulate velocity field. And this also is sort of like volume averaging. Okay. The other hand I was talking about is the ensemble average. Ensemble average is nothing but you can pick a point and you average over all the realizations. Now, in this simple example, it's uniform distribution with some structures, and that the way I've drawn is that some structures, and I don't know where it's going to appear. So when I average over gazillion realizations, sometimes I will be in a cluster, sometimes I may not be in a cluster, but it doesn't matter where I pick the point. Therefore, the ensemble average will be the same everywhere. So, in this particular example, it is not always the case. So, sometimes the ensemble average can have variation in one direction. It could be function of time, etc. So, the concept I want you to think is, yes, there is a lot of RANS kind of simulations. People do ensemble average or time average, and they do simulations of that kind, where one of the things is that it erases or it averages over all turbulence. Now, the interesting thing is that it averages over all these structures of particulate stuff. Okay? So, when you do ensemble average, you lose a lot of information, but sometimes it is useful, sometimes it is not. So, I want you to keep that in mind. Therefore, I like personally a lot of volume averaging, sort of like large eddy simulation kind of stuff, where you coarse grain, you still have lots of structures that are around, but that still has this question, what is the length scale are you going to average? But one simple answer is, you will know how big a grid that you can afford. Okay? You have a tank of meter by 5 meters, and let us say that you can do only simulations of say 100 by 100 by few hundred grid points. You know exactly what your volume average is going to be. So many a times your averaging scale is dictated by what you can compute kind of stuff. Okay. Yes.
So I have a question regarding LES that you spoke about. So in such a condition, when we take subgrid scale modeling, what are we really looking at in that case?
Well, you want to capture all the micro scale physics that is happening within that little averaging volume. It must be embedded in your governing equations. So, I am going to talk a lot more about this. This is just a general discussion of what are the challenges that are ahead of us. Okay. So, I have not gotten to the final punchline that we will get how to formulate equations, but last 2 hours we are just laying the groundwork of why multi-phase flow will be challenging. So, the point I am trying to make is, we all know in LES, large eddy simulation, we erase all the subgrid turbulence, but now you want to think there may be structures, clusters happening within your grid, and that depends. Say if you are doing a LES of a volcanic eruption, your grid is 10 meters by 10 meters by 10 meters, something like that. There are people who are doing large eddy simulation of a volcanic eruption. They have a lot of challenge. I mean, what is happening in that big grid, everything must be, they must understand and put it in their modeling. Okay. And then on the other hand, I said that you could do coarse graining or average over some volume. Sort of like, imagine that you have the flow and then you sort of fuzz out the details and you look at the flow. So, all the details of where the exact particles are is forgotten, but you still will know where there are more of them, where there are less of them, etc. Okay, so those are the two different approaches. The ensemble average will give you equations that are similar to RANS models. Okay, you will have ensemble average equation for the fluid and ensemble average equation for the particles. The volume average will give you, it is more like LES. So, you are talking about one particular realization and you have to integrate over time and so on. And there again you get the coarse grained fluids equations and coarse grained particle equations. So, ensemble average equation does not tell you about one realization, one run. It only can talk about average, and it applies for the entire ensemble. On the other hand, the volume average approach, those equations that we will derive later, it applies only to one particular realization. Okay. Since you average all turbulence and all variations of particles in ensemble average, it will have all the symmetries of the problem. Okay. Sometimes the problem may become one dimensional because that is the only direction the average changes. Often it becomes steady. Okay. So, ensemble average equations allow you to solve one dimensional problem, steady problems and so on. Now, even if the problem is nominally one dimensional and steady, if you are looking at one realization where turbulence is happening and the particles are non-uniformly distributed, volume average will always be three dimensional and time dependent in a turbulent flow. Okay. Therefore, like in LES, you can't have a steady LES or one dimensional LES. You are stuck with solving 3D time dependent problem, but you will describe a realization in greater detail, okay, with coarse grained turbulence. So, you will still have turbulence at the larger scale, and you will also have description of the particles on the larger scale. Okay. So, here ensemble average, it erases every sort of randomness. So, you are only dealing with average quantities, okay, mean, RMS and so on and so forth. You will have equations for them. Here in volume averaging, you only average details that are smaller than your scale, that filter that you are going to choose. So, the scale on which you are fuzzing out the problem, and I said that that depends on the grid that you choose. You cannot have anything smaller than your grid resolved. So, you only resolve things that are bigger. The ensemble average approach therefore is easier to solve, okay, because all this turbulence has been erased. It is much smoother flow. Like I said, that it could be steady, it could be one dimensional. So, often computationally it is easy to solve. So, what is hard about ensemble average approach, like in Rand's approach, is that now you have closure models and they are difficult. Okay. Whereas here you may have difficulty because it is a time dependent 3D problem. It is hard, but I tell you the volume average approach is still much cheaper than really trying to resolve the flow around each particle. Okay. There you got to put around each particle and track the particle. That is really hard. Okay. So, volume average gives you tremendous advantage, but still you have to solve a 3D time dependent problem. Okay. And since you are averaging over the volume, you still need closure models. So, the two kind of closure models that I will talk about are things that are mainly suitable for volume averaging approach, but also for ensemble average approach. Okay. So, those are the main things that I want to point out. Again, I want to emphasize the point that ensemble average will have all the symmetries of the problem. In other words, if you are dealing with a nominally steady flow, even though the flow itself is time dependent, if the statistics are time independent, then ensemble average equations will become steady, whereas volume average will not have that symmetry. And the same thing about spatial symmetries, whether your problem is homogeneous in certain directions, only the ensemble average will preserve the underlying symmetries of the problem, whereas you have to solve 3D time dependent problem when you just coarse grain it, or when you use volume average approach. Okay. So, that is where I want to stop this particular lecture, and I want to go to the next lecture, because this is just a continuation of finishing of what we talked about last time.
We take these particles and take Earth over a time period. What is it? In ensemble average, we take these particles and take Earth over a time period.
In fact, we do not look at individual particles. So, let us say you have a experiment, okay, like a bucket with a stirrer with lots of particles. Now, in ensemble average, we are asking you pick any point within the bucket, and then if you were to repeat that experiment zillion times, some realizations will have a particle there, some realizations will not have a particle. Let us say 10% of the realization had particles and 90% you saw at that point fluid. Well, right away you know right there at that point volume fraction of particles is 10%, because only 10% of the time you see it. So, you can move to a different point and you do the same ensemble average. So, you can find the ensemble average will tell you what's the probability of finding a particle there. So, there is no individual particle once you do an ensemble average. You are just talking about an average, but you will know that, hey, this spot has 10% volume fraction. Some other corner, if particles hardly ever come there, there the volume fraction will be low. Somewhere else. But what I am trying to say is the ensemble average erases all the details about any particular experiment, what's happening. If there is a wave of high particles sweeping the region, you won't know all those details. Ensemble average will become steady state sometimes, will become homogeneous. There may be variation only in one direction. So, if you take a fluidized bed, you will find that it's steady and everything varies only in the vertical direction. Whereas, when you do local averaging, you will retain all the turbulence, etc.
Sir?
Yes.
In the last lecture, we were discussing about particle vortex interactions, and there we said if Stokes number is less than 1, the particle will simply follow the vortex.
Very much less than 1.
Very much less than 1.
Yeah. See, what happens is particles, Stokes number very large, it doesn't care about the fluid. It's sort of like baseball or cricket ball being thrown. They just follow what you initially, what velocity you give. So, that's very large Stokes number. On the other hand, nanometer sized particles, they just will follow the fluid. It's only Stokes number around 1, they get spun out and do all sorts of interesting stuff. Your question, I never let you ask the question. Yeah.
So, the question I was about to ask is if we want to measure the velocity of a vortex, and let's say we use these particles, the micrometer particles, for like let's say PIV measurements we do. So, how I make sure that whatever particles I am using will give me the exact velocity of the vortex?
Yeah, excellent question. So, the answer is, if you want to take the particle velocity and call it the fluid velocity, you have to make sure that there is no slip. They follow each other. So, easiest way, you calculate the flow time scale. Okay, what's the time scale on which the vortex is spinning? So, if you know the vorticity, you can take inverse of the vorticity. That gives you the time scale on which fluid goes around. Now, you calculate tau p, take the ratio, that's the Stokes number. If the Stokes number is 10 to the power minus 2, then you can safely say the particle is following. Now, if Stokes number is order 1, then the particle is still obeys the fluid, but it's a little adamant. It just keeps going out, or if it's lighter, it will come inward. I will show you later in this lecture that you could calculate from the particle velocity what should be the fluid velocity, because still it's not like baseball being thrown. It still obeys, and whatever it does is dictated by the flow, but it has its own a little bit of its own mind. So, it doesn't quite exactly follow the fluid, it has slight slip, and that depends on the Stokes number. So, particle velocity, we will write later in this course, is equal to fluid velocity plus something that depends on Stokes number. Okay? And if we know what that thing is, then if you measure the particle velocity, you could back out and find what the fluid velocity is. So, it can be a very useful thing for PIV, especially on high speed flows, because it's very hard to make the particles smaller and still have a measurement. So, this is an important issue in high speed PIV measurements, is how do you get the true fluid velocity from the particle velocity. Yeah.
Sir,
Yeah.
Regarding whatever underlying symmetries are there, so you said ensemble average will take
We'll
care
preserve
of it.
that, yeah.
So what about quasi-steady volume averaged approach? Like if we wait until the time derivative goes to 0.
Yeah. No, you see, we want to be very clear about whether we are talking about statistics, time dependence of statistics of the individual flow. Say you have a big fluidized bed and you start it, and then you wait for the transients to die, and then it's running for 15 minutes, and then you see, then you may say, well, all the transients have gone. But if you were to take pictures of the flow, it keep changing because the flow is turbulent. What you were interested in was the statistics to reach a steady state. And typically you call it not even steady state, you should call it stationary state. The statistics has reached the stationary, it does not change, the statistic does not change anymore, but individual realizations will be time dependent. When you do it ensemble average, it becomes time independent in such a problem after you have reached stationary state. But if you take a particular run of that experiment and you say, I am just going to fuzz out, like you step back and you do not look at all the details, it is all changing in time. You cannot remove that. Your statistics may be stationary, but when you watch the flow, it will ever be time changing. Okay? So, ensemble average, that is why will be time independent, because you have average over many realizations, and it will preserve the underlying symmetry, whereas the volume average will not. Did that answer your question?